In this section, we'll study techniques for noise data analysis, such as weighted least squares and RANSAC. Scene analysis is concerned with the interpretation of acquired data in terms of predefined models. It has two subproblems. First one is finding the best model, which is a kind of classification problem. And the second one is the computation of the best parameter values, which is a parameter estimation problem. Traditional parameter estimation techniques optimize the model to all data points, such as in least squares. Those techniques are simple averaging methods based on the smoothing assumption. The assumption is there will always be good data points enough to smooth out any gross deviation. However, in reality, the smoothing assumptions does not hold in many applications. That means the data set may involve gross errors such as noise. So in order to get more reliable model parameters, there must be internal mechanisms to determine which points are matching to the model inliers and which points are producing false matches, outliers. Here we have weighted least squares. When you get data points, then you may see that some points are more important and more reliable than the others. In this case, for those important points, you may try to give larger weight. This is the idea of weighted least squares method. That is an least square method which involves a weight metric W. The weight metric is often given as a diagonal metric like this. These weights can be decided either manually or automatically. Here is an algorithm for weighted least squares. For given data set xi, yi, the best fitting curve can be found by solving an algebraic system given in this way. We formulated this form of system earlier. When a weight metric is applied, then the system can be rewritten in this way. Just we simply multiply the weight metric. Then the corresponding normal equations, weighted normal equations, can be formulated in this way by multiplying X transpose. Once this is invertible, then we can get the parameters uniquely. See this example. Given data, and we want to find the least squares line with and without a weight. When a weight is applied, the weigh the first and last data points by 1/4. Okay. Now, if you see the data, okay, in fact, we can plot here. Now, it's around the line for interior points, but for boundary points, is quite perturbed. So we may consider these two boundary points are not reliable. It's not easy to discard these points because when in reality, when you try to get a data set, then every point is money. Once you pay the money, then it's not easy to discard those points. So you may try to use it with smaller weights. So that's the idea here. Now, LS is output of the curve fitting in standard way, having all the way same weight. Now, weighted least square is using this weight metric. For first one and last one, the weight is 1/4, and inside the interior points have the same weight 1. So let's see the results. These are apparently quite different. Okay, when we are using weight, then we have that solid curve, and without using weight, we have that one. So now here, weighted least squares is more reliable, right? Once we assume that these 2 points are outliers. Now we'll go to RANSAC, Random Sample Consensus. RANSAC is one of the most powerful tools for the reconstruction of ground structures from point cloud data sets. The algorithm utilizes iterative search techniques for a set of inliers to find a proper model for given data. Here is an algorithm that is invented by Fischler-Boles in 1981. Okay. Now, X is the data set. Error tolerance tau e is used to as a radius between the model. So I'll explain this one, how it is used. And now stopping threshold is eta and maximum number of iterations, capital N. We start with the first step. First, select randomly minimum point set required to determine a hypothesis. The minimum point set means that minimum number of points. For example, if your model is a line, then if you choose 2 points, then you can decide the line. So that minimum point set will include only 2 points. So we select randomly 2 points to form a minimum point set and generate a hypothesis P. Hypothesis is now a model. The line is made in, and compute the hypothesis consensus set fitting within the error tolerance. Once you constructed a line, then here in radius tau e is used to get a strip like that, and then that is now we count the points inside this strip. So in this way, tau e is used. So that from the data set and using the model and using the tolerance, so it is a radius of that, and we collect the points inside this strip. Then that is the consensus set. Now we count the number of points inside the consensus set. Then once it is larger than a certain number, so eta is used to the threshold, so it's portion. For example, 0.9, then 90% is larger than or equal to the 90% of the original data points. Then we re-estimate a hypothesis and stop Otherwise, we go number 1, first step, and repeat. And after n iterations, once we cannot find any hypothesis, any inlier set, so that here it is not, it is satisfied. If there is no such consensus set, then among the searched, we try to choose the set having largest number of points. So in each iteration, we keep the best one, so that once at some point it is satisfied, then return the best one and stop. If not, then we continue up to n iterations, and eventually we return the best one. Okay. Here, let's set a hypothesis for a regression line. When we choose line, then we need 2 points. And from 2 points, we can easily get here the model, or in this way. But that can be made easily here by using the technique. The slope can be measured by using change in y divided by change in x. You did this one from high school, and you can decide the model. And for the consensus set C, now that is the collection of points. So that from the point to the line, that is the formula for the distance between xi, yi to the line. I guess also you learned it from high school. The distance is bounded by tau e, then is a part of the consensus set. Okay. Here we have a note for implementation of RANSAC. In step 2, the hypothesis P is the set of model parameters rather than the model itself. That means that rather than model itself, y equal a plus bx, probably we may save only a and b. It's okay. In third step, we need only a and b. Right? Now in step 3, the consensus set can be represented more conveniently by considering C as an index array. That means that C is an index array, so that once xi is in C, the consensus set, which means for xi, this inequality is satisfied, then at ith position we put 1, otherwise we assign 0, so that we try to collect the points corresponding the index value 1, then these are points of inliers. So it is quite conveniently collect the points for inliers. Okay. We have a remark for the RANSAC. The inlier function in step 3 collects points whose distance from the model is not larger than tau e. So the distance can be interpreted as an automatic weighting mechanism. As a matter of fact, for each point xi, once distance from xi to the model is bounded by tau e, then we try to set the weight is 1, and otherwise the weight is 0. Then the re-estimation in the last step, and when we just before stopping, the hypothesis can be seen as an parameter estimation with corresponding weight metric. So the the parameter estimation in the RANSAC can be considered as weighted least squares. Okay. The basic RANSAC algorithm, it is an iterative search method for a set of inliers, which may produce presumably accurate model parameters. However, it is problematic and often very erroneous. The main disadvantage of RANSAC is that RANSAC is unrepeatable. It may yield different results in each run so that none of the results can be optimal. However, it is simple in implementation and also efficient, so that people like it. People like simple algorithms. See this example. Now we have two different data sets. Blue points are inlier points and red dots are outliers. Once we are using all the points, then here we have red line on both sides. And if we are using only inlier points, then we have here blue line from the least squares. Now we use RANSAC, then here cyan dashed line is made and as from the output of RANSAC. Now as you can see here, now these lines are a little bit different from the desired one. And now if we run, and then each time, sometimes it's very good, but sometimes quite different. Sometimes you can see very with a very large perturbation, such a line is made. So I try to measure the changes after running 1,000 times here. Now from RANSAC, and I collected outputs, the 1,000 output, and try to measure the standard deviation for this model, for the intercept and for the slope. So that is, now for left data set is data set 1, and we have here standard deviation for the y-intercept, this value. So its error is large. And for slope, and again large, and that is average computation time. Now for right side data set, here the intercept is 0.1, so it's not so much accurate. Error is really observable, and slope has such error, standard deviation, and this is computation time for the data set in the right side. Okay. We have here a summary for RANSAC. RANSAC is neither repeatable nor optimal. In order to overcome the drawback, various variants have been studied in the literature. For variants, we can consider this maximum likelihood estimation sample consensus. That is called I guess that must be MILSAC. So not easy to pronounce, but anyway, MLESAC, and here progressive sample consensus, there's PROSAC, and recursive RANSAC, so RANSAC. Yet people don't know how to overcome the drawback completely. And in fact, I published a paper this year, and that's called RUSAC, IUSAC, and RUSAC, and that is now optimal. We are using iterative update rather than iterative search, and we can get some convergent the variant of RANSAC. Along with that, we can improve the computation time and accuracy a lot. However, anyway, here currently RANSAC remains a prevailing algorithm for finding inliers. And even though people made such variants, RANSAC is simple and efficient, so that people like it. Okay? That's the end of the section. Thank you.